So today we're going to start talking about the three-phase power, which is the last module for this course. And today specifically, we are largely just going to go over terminology and an introduction. This will be our first and pretty much only class meeting where we're going to do almost no math whatsoever. All right, so let's call this introduction to three-phase. And you're probably going to see me write this as 3P from now on, or actually more likely 3 and then a phi. Circuits. So the first thing that I want us to look at would be a simplified representation of a single phase circuit. Okay, that's because this is what we're most used to dealing with from a practical perspective. If we were to plug anything into an outlet in our home or something like that, that is literally what a single phase circuit would look like. So for a single phase circuit, we might have something like this. So over here on the left-hand side, I'm going to put a sinusoidally varying source that I could represent in the time domain, or excuse me, in the frequency domain as some RMS phasor voltage VP with an angle of theta V. And then I'll give myself a pair of terminals here. Okay. And I'm going to call this terminal A, and this would be terminal N. I'm going to have a run of what I'm going to refer to as a transmission line, but really it's just a conductor. It's going to go to a terminal uppercase A and uppercase N respectively. And then over here on the right-hand side, I'm going to have some load impedance, which I'm simply going to call ZL. Okay. So let's look at a couple of things here. Okay, so the first thing I'm going to do is I'm going to subdivide this circuit, as it were, into three distinct sections. So over here on the left, we have our source section, okay? So in the context of a circuit in our home, effectively this would be the voltage that's being provided to the main breaker in our load center in our home. Realistically, that's not technically true because in our home, well, I mean, it could be this. So in our homes, typically speaking, even though we get 120 volts RMS out of our outlets, our homes are supplied with 240 volts RMS in a split phase system. So we have a single phase, but that 240 volts is split into positive 120 and negative 120. And so we can power low current draw loads with just 120, and then higher current draw, higher power loads like our ovens, dryers, and all of that kind of stuff with 240. But anyway, that's another bag of cats. So the source side of here, like I said, is representing effectively the voltage that's being provided to our home and that we have access to in our breaker panel. Our transmission lines, which is what this network here in the middle is, would then typically be what we're going to call a hot wire and a neutral wire. And then lastly, we would have our load, which is just whatever we have plugged up into a receptacle in our home. So it might be a computer or a fan or a space heater or a microwave or something like that. But this is the basics of a single phase circuit. Typically speaking, in this room, like we see, we have what are called duplex receptacles, which means there's two outlets connected electrically in parallel to each other. So we could just tack another load on here if we wanted, and this would literally be representative of what's going on with a single outlet. And then we might see further wires attached and then other outlets down the line and so on and so forth, controlled by a single breaker. Okay, not particularly important for what we're talking about here. Just trying to put things in context of physical systems that we're used to. Okay, so that's the basis of a single phase circuit. So now let's look at one of numerous different representations of three-phase circuits that we're going to face, okay? So this is going to be an example of a three-phase, three-wire system. And so what we're going to have is a three-phase voltage source. Let me make sure I actually gave myself enough room here. Might look something like this. So here we have some RMS phase voltage VP with an angle that I'm going to call theta A. We'll have some RMS phase voltage VP with an angle of theta B connected to our B terminal. And then third voltage source, VP angle theta C connected between our C terminals. And once again here, we've got a transmission line network connecting lowercase a to uppercase a, lowercase b to uppercase b, and lowercase c to uppercase c. And then we have a three-phase load over here. So I'm going to call this ZL, so this is a load impedance, and then the subscript A is just corresponding to the A phase of the load. Then we might have ZLB here. And ZLC connected here. And once again, we can break this thing up into the same basic structure. So source, transmission line, and load. We're going to make a couple of observations. So first thing, I'm going to call this my A phase line. Usually it would be called a conductor, but there's not enough room to write conductor there. Here's my B phase conductor and my C phase conductor. We do not, in this particular system, have a neutral conductor going from the source to the load. Some three-phase loads some three-phase systems utilize a neutral conductor, others do not. Just depends on the application, how much imbalance we're expecting, et cetera, and we'll talk about all that in a little bit, okay? So we've got our source over here, our load over here, and once again in the middle, our transmission lines. All right. So if we were to compare, let me try to shrink this a little so we can see them both at the same time. Might have been too much. If we were to compare these two systems, they are incredibly similar to each other, right? So why would we ever want to use a three-phase system versus a single-phase system? So let's make an assumption here. The load impedance ZL is absorbing some amount of average power. And let's say that each phase of the three-phase load is absorbing the exact same amount of average power as the single-phase load, so that we have an apples to apples kind of comparison here. Why do you think a three-phase system would be used if the exact same amount of power is getting delivered to the load? So it's not going to be supplying more power in general, because I already restricted us to have a caveat that the same amount of power is being delivered to each load.
About being more efficient.
So it depends on what you mean by efficiency. And it also depends on what you mean by balance. So that's something that, concept of balance in the three-phase system is something that we're going to talk about a little bit today, and it's effectively what we're going to devote our entire next class meeting on. Okay. There's something that's actually kind of obvious here that you guys aren't quite seeing, and it's subtle, okay? So think about this in the context of infrastructure costs, okay? To deliver a certain amount of power to a single phase load, it requires us to have 2 wires. To deliver 3 times as much power to 3 loads, like that we have on our 3-phase system, it requires a sum total of 3 wires, which means we deliver 1.5 times as much total power for, or excuse me, 3 times as much total power for only 1.5 times as many wires. So it's physically cheaper to set up a system like this, which is why 3-phase power is usually used. Okay. The infrastructure costs in sending power over long distances and all of that kind of good stuff are significantly cheaper in a 3-phase system than they would be in a single-phase system, because it literally takes less wires to do it. That is the principal advantage of 3-phase power. Now, in the context of specific loads, if we were dealing with, say, an electrical motor, there is another extremely huge reason to use 3-phase power, okay? So I'm going to scroll back out here, and I'm going to hit you guys with the average power relationship. We're going to derive these things later. So for a single phase system like this, the average power, actually, hold on, let me do it this way. The instantaneous power is VP IP times 1 plus cosine twice omega t plus theta v plus theta I, where this current IP angle theta I is the current that's flowing out of the positive polarity terminal. That's nothing more than the instantaneous power relationship that we developed in circuits 1, except that I put everything in terms of my RMS effective values for voltage and current, as opposed to doing 1/2 VM IM. It's the same, literally exact same relationship, okay? So we have an instantaneous power here. What can we say about this instantaneous power? Does it vary in time? Yeah, it absolutely depends on time. There's a time dependency right here of twice omega t. So if we have an electric motor or something like that connected to a single phase system, the power that's getting delivered to the motor is constantly changing. What do you think that does to the motor? Causes it to surge constantly, which means the torque developed by that motor is also going to be changing in time, okay? Now, the instantaneous power developed by a three-phase system, and it'll be a couple of days until we derive this, is literally just going to be 3/2 VP IP cosine theta V minus theta I. And actually, there's a mistake up here, but it's fine. This should also be cosine theta V minus theta I. That's what I get for freestyling part of my lecture. The instantaneous power developed by at least a balanced three-phase system is constant. So the instantaneous power and the average power are literally the exact same thing. We'll go through this mathematically in a couple of days, but from the context of a load like an electrical motor, if the power delivered to it is constant, the torque developed by it is constant, which means our motors don't vibrate, don't do all kinds of weird things that cause mechanical damage to it. So in a three-phase system, a balanced three-phase motor can effectively run for practically ever. Literally across the hall from us in the power lab, we have three-phase motors that were donated after World War II. They're still in operation. So they are 80 plus years old, require almost no maintenance whatsoever, as long as you don't go around messing with the coils and all that kind of good stuff. They will practically run forever. So that is another huge reason that three-phase power is used in industrial settings. Okay. All right, so we are going to look very briefly at how this portion of our system, the voltage source, works. So let's call this three-phase voltage generation. So I am going to attempt to draw something here. And what I'm attempting to draw is a very simplified representation of what's called a synchronous generator. So synchronous machines match the input frequency exactly. So the electrical frequency that we input, the mechanical frequency is effectively the same thing. They are locked into each other, which is why they are typically used for generators, so that we don't have to worry about frequency drift and all of that kind of good stuff, okay? So in a rotating electric machine like this, we have two main pieces. We have a stator, which is the stationary part of the rotating electrical machine. And then we have the rotor. So I'm going to start by drawing the stator. And this is realistically just a big cylinder, effectively. There's a bit more to it than that, but as far as our representation goes, that's the gist of it. All right, so this thing right here represents the stator. Once again, this is just the stationary part of our rotating electrical machine. And embedded into the stator are usually coils of wire, okay? So I'm gonna say that this is a very simple machine. And so we're gonna have one coil of wire right here, that's gonna correspond to the A phase of our system. And so I'm gonna put a circle here like so. I'm gonna put the little letter A that's letting us know that this is for the A phase. And then exactly 180 degrees mechanically or physically away along this circle is the return path. I'm going to do that one in gray. And I'm going to call this A prime. So effectively, if we were passing a current into the board in A, we're going to see a current coming out of the board in A prime. So we have a send path and a return path for this coil. Okay. And so we're also going to have access to these terminals external to the device. So I'm going to call this guy right here A. And then here's my neutral connection. And I'm just going to bring that down over here. And I'm not going to give it a label just yet. Okay. So physically, 120 degrees away along our cylinder from A, we are going to have a B coil. And I'm going to draw this one in blue. And then 180 degrees across, we'll have the return path. Once again in gray, and I'll call this one B prime. And then 120 degrees away from both A and B, so over here on the right-hand side, we'll have a C coil, which I'll do in red. And 180 degrees away from C, we'll have our C prime return path. Let me go ahead and now kind of wire things up a little bit, okay? So I'm going to tie all of those prime denoted terminals together. Like so. And I'm going to call that common point of interconnection my neutral terminal for this voltage source. Okay. Then I'm going to take my C conductor. It's going to jump over that neutral path. And so I'm going to have access to a C phase terminal. I'm going to do the exact same thing for my B phase. Like so. So right now, effectively what I have is 3 different inductors, because we just have coils of wire kind of tied together. And then we have access to their point of interconnection, which is our neutral terminal, as well as the other leg of each inductor, which we're calling our A, B, and C phase connections there. Okay. So this is how our stator is set up. Okay. This is commonly referred to as a Y-connected machine. And now we're going to talk about our rotor. Okay. So in a real synchronous machine, our rotor is an electromagnet. That would be annoying to draw and would require more coils of wire, would just make this even more confusing. So I'm going to replace the electromagnet that forms the rotor with just a permanent magnet. So something akin to this. So we've just got some permanent bar magnet like so, where let's call this the North Pole and this the South Pole of the magnet. This dot in the middle is a pin so that our magnet is free to rotate. So how many of you guys have had Physics 202? All right, almost all of you. Great. So if I have a magnet, it generates some amount of magnetic flux. We all okay with that? Anytime I have magnetic field lines, if I can bind them to an area, we get a magnetic flux. So at some points in time, the magnetic flux that is passing through coil A will be at its maximum. And then as our magnet rotates, the amount of flux that's passing through coil A is going to gradually decrease until we have a maximum value of negative flux because our field has changed direction. And then it's going to continue cycling between maximum, gradually decaying down to minimum, gradually increasing up to maximum over and over and over again. So what happens when the amount of magnetic flux that passes through a coil changes? Faraday's law of induction says that whenever the flux, or whenever the magnetic flux through a coil is changing, we will induce a voltage, and then if that's a closed path, current will flow, okay? So right now we have everything open circuited. So I'm going to put a voltage here between my A terminal and my N terminal, and I'm going to call this voltage VAN of T. We're going to see a similar voltage between my B terminal and my N terminal that I'm going to call VBN of T. And we'll have a voltage between my C terminal and my N terminal that I'm going to call VCN of T. And now I'm going to attempt to draw these three voltages. So I'm going to pre-apologize for how crappy my ability to draw a sinusoid is. So our vertical axis is the magnitude of our voltage, and the horizontal axis will be time. Okay. So let's say that we start our A phase going at exactly t is equal to 0. Okay. So we should see something like this. So since the magnetic flux that's passing through the coil is changing sinusoidally, because we're simply spinning it, the induced voltage should also be sinusoidal. So our voltage VAN of T could be expressed as some magnitude. So I'm going to call this VM lowercase a. So this is the magnitude of the A phase voltage, cosine omega, the speed at which our rotor is spinning, T, plus theta AN, where we made an assumption here that we're starting at 0, but we might play around with that. Okay. Now, based on the direction that my rotor is spinning, so if we start out with our magnet pointed directly up so that the flux passing through coil A is at its maximum, with our magnet spinning in a counterclockwise direction like we have indicated, the next coil that it's going to see is the B phase, right? And so what we're going to see is that the voltage induced across our B phase coil is exactly 120 degrees lagging the voltage induced in the A phase, because the B phase coil is physically 120 degrees out of phase with the A phase coil based on the construction of our generator. So 120 degrees out of phase means that we should be hitting our peak value about right here. Something like this. And VBN of T is going to be some particular magnitude. So let's call it VMB cosine omega T plus whatever theta AN was minus 120 degrees. And if we combine these two things into a single term, we might call this, theta BN. So our B phase voltage is lagging our A phase voltage by exactly 120 degrees based on how our generator is constructed. When we go another third of a cycle around, we should see that our C phase voltage will now be at its maximum. Right. So somewhere about right here, I think. Where this voltage VCN of T is going to look like VMC cosine omega T plus theta AN minus 240 degrees. And this total phase angle here would be commonly referred to as theta CN. So the B phase is lagging the A phase by exactly 120 degrees. The C phase is lagging the B phase by exactly 120 degrees, and the A phase by exactly 240 degrees, all because of how this machine is constructed. Now, if the coils in the A, B, and C phases had the exact same number of turns, then the magnitude of our induced voltages would be identical. So VMA would be equal to VMB, would be equal to VMC. This is practically always going to be true, because these generators are effectively built by robots to make sure that those coils have the same physical characteristics and they're all made out of the exact same material, all of that kind of good stuff. so as to ensure that those voltages are going to be as close to each other in magnitude as they can possibly be within manufacturing tolerances, okay? So VMA, VMB, and VMC are all effectively equal unless somebody goes in and intentionally messes something up. So what we have here is what's called a positive phase sequence. So it goes from A to B, then to C over and over and over again based on the direction of our rotation governed by omega. A negative phase sequence set of voltages would be what would happen if we allowed our rotor to spin in the opposite direction. So it would hit C first, and then B, and then A. So if we go A, B, C, that's what we call positive phase sequence. If we go C, B, A, that's what we call negative phase sequence. They're literally the exact same thing, except that now, for a negative phase sequence system, C would lead B by 120 degrees, which would lead A by 120 degrees, and so forth. So the only difference it would make would be to change those signs on the minus 120 and minus 240 respectively. They'd go from negative to positive. So for the intents and purposes of this class, we are only going to be dealing with positive phase sequence systems because a negative phase sequence system behaves literally the exact same way. Everywhere you hear the word lagging, replace it with leading and you're done. Okay, so no real point in wasting a bunch of extra time on that. All right, so now let's talk about different, actually, before we move on to the next topic, anybody have any questions about three-phase voltage generation? I understand I glossed over a whole hell of a lot of things that you guys, some of which you've learned in your Physics 202 class, others of which you will learn in your E&M classes here in electrical engineering, and definitely if you take the course on electric machinery and power electronics, ELEN 484 in your senior year. We'll go into great detail about how synchronous generators and all that kind of stuff work and why they work the way they are. But anyway, any questions before we move on from this? So for all, for this class, we are going to assume that every three-phase voltage source is effectively similar to this, in as much as it will be a balanced source where all of our magnitudes will be equal and all of our phase angles will be separated by exactly 120 degrees. Okay, so let's now talk about source and load configurations. Wish this would zoom correctly. Yeah, screw it. All right, so the first thing that we are going to look at is a Y connected source and how we're going to represent that. So a Y connected source physically would look very similar to what I literally just drew. In a circuit schematic diagram or something like that, there are two different ways that we can represent this, one of which I absolutely hate, and it is unfortunately the conventional way that it is done. And then another way, which I absolutely prefer. You don't see it in many textbooks or anything like that, but to me, it is much, much clearer to use for analysis purposes. Okay. So the conventional method would look something like this. So here is going to be my A terminal. Here is my B terminal. And I'm going to put a voltage source here. And this diagonal orientation like so. I'm going to put another voltage source down here. And now let's take some time to define a few things, okay? So this point of interconnection between all three of my voltage sources is my neutral, just like we had earlier. And so I'm going to call this N, and I'm going to make a note here that this is optional. What I mean by that very specifically is that we may not have physical access to connect a neutral wire there. So that point of interconnection between those three windings very much exists. It's just we may not be able to connect anything directly to that point. So that's why I'm calling that an optional thing. Okay. So the voltage that we're going to see between the A terminal and the N terminal of this device, I'm going to put the positive polarity on the A side and the negative polarity on the N side. And so we're going to represent this in the RMS frequency domain as an RMS phasor voltage VAN. And I'm going to do the exact same thing for all of my other voltages. So the neutral conductor will always be my negative polarity terminal, which makes this voltage VBN and this voltage VCN. So this is the conventional way of drawing a Y-connected source, and I find it to be incredibly bothersome. So instead, I prefer to draw them exactly how I did earlier on, like so. So here's my A terminal. This is going to be voltage VAN. Here's my B terminal. This is voltage VBN. Here's my C terminal, VCN. And then I'll draw my neutral terminal down here at the bottom, like so. One thing that I want to point out, because I don't know that I've mentioned it yet, when we are on the source side of our system, we are going to use lowercase subscripts for everything. And when we are on the load side of the system, we are going to use uppercase subscripts for everything. And this helps us to easily sort out whether we're looking at load side quantities or source side quantities, okay? I've been doing that this entire time. I just want to make it super obvious to you all right now if you haven't quite noticed. Okay. So here we have our two different representations of a Y-connected voltage source. And now I want to define some quantities, okay? So the first quantity that I want to define are what are called phase voltages. So a phase voltage is simply the voltage drop over one phase of a source or a load. So I'm going to ask you guys, what do you think the phase voltages in this particular voltage source are? Taking longer than I had hoped. What was that? I would like for you to identify the phase voltages in this system. based on our definition, a phase voltage is just the voltage drop across one phase of a source or load. Absolutely. Why does it have to be more difficult than that? So our phase voltages here are literally nothing more than our voltages VAN, VBN, and VCN. 100% agree. Thank you, David. Now let's talk about line voltages. So a line voltage is the voltage drop between the transmission line terminals of a source or load. So effectively, we literally just measure the voltage drops across the terminals of our system, okay? So I would see a line voltage of V lowercase a, lowercase b between the A and B transmission line terminals. I would see a line voltage of V lowercase b, lowercase c between the B and C transmission line terminals. And I would see a voltage VCA between transmission line terminal C and transmission line terminal A. Okay. So another thing that I want to point out, just in case it has not been obvious to you yet, the first letter of our subscript for any of these voltages is always at the positive polarity terminal. And the second letter of our subscript is always at the negative polarity terminal. Now you may be asking yourself why we chose VAB versus VBA or VBC versus VCB, etc. All of that will be revealed when we start playing around with the math of these things, okay? These are going to be our line voltages for this system. So I'm going to call this VAB, VBC, and VCA, like so. And I'm going to label them over here on my other representation. So once again, our line voltages are literally just measured between our transmission line terminals. So here we have VAB, VBC, and VCA. So now let's talk about phase. Actually, before we do that, I want to mention something here. Okay. So in this class, we are going to refer to everything as either a phase voltage or a line voltage, according to these definitions that I have given you. In industry, you might hear things like a line-to-line voltage. That is literally the voltage measured between two transmission lines. That is the exact same thing as what we are calling a line voltage right here. You might also hear something about a phase to neutral voltage. That would be the exact same thing as the phase voltages that we see here. However, in a moment, when we look at a delta connected load, we will see that there is no such thing as a phase to neutral voltage because there literally isn't a neutral connection. So my preference is to actually use the terms phase voltages and line voltages versus the common industry terms of line-to-line voltages, phase to neutral voltages, or line to neutral voltages, just because they are applicable for all of the different configurations that we're going to see. They're not specific to any one particular type of source or load. So I just wanted to make that very clear. It will actually introduce less confusion in the long run if we don't have 6 different ways to talk about the same damn voltage. Okay, so phase currents. So a phase current is simply current flowing through one phase of a source or load. And so this is another place where textbooks and I tend to disagree. It's literally just a direction thing, nothing other than that. I personally prefer to have my phase currents drawn as if they're flowing into the positive polarity terminal of each phase, regardless if I'm on the source side or the load side. Most textbooks draw phase currents flowing out of the source and into the load. I'm going to draw them flowing into the source and into the load so that we don't have to worry about subscripts getting backwards and all of that kind of weird stuff. So we will have a phase current here. That is IAN. We'll have a phase current here. That is IBN. And we'll have a phase current here. That is ICN, like so. And let me represent those phase currents over on this diagram. So they're just the currents that are flowing towards the neutral connection. And then lastly, and this isn't actually something that we're going to be able to draw on our diagram, we also have a quantity called a line current, right? So if we have phase voltages and phase currents, we should have line voltages and line currents. So a line current are nothing more than current flowing through each phase of the transmission line network. Let me know when you finished writing down my little definition here so we can scroll back up and kind of identify these. All right, so because I'm only dealing with a voltage source here, I don't really have a transmission line network that is specified, so I can't represent my line currents on this diagram. However, if we scroll back up to our simple 3-phase circuit here, I can definitely represent them here. Okay. So this is what I'm going to call my line current, I lowercase a, uppercase a, okay? Because it's flowing from the source side to the load side, it gets a subscript of lowercase a, uppercase a. Very similarly, we would have a line current I lowercase b, uppercase b here, and a line current I lowercase c, uppercase c here. So transmission line, or excuse me, our line currents are probably the easiest thing to sort out because they're literally just the current flowing down the line. Okay, so that's the least confusing of our different things that we are going to be representing here. Okay, so before we move on to our next source configuration, do any of you guys have any questions about any of this terminology or anything like that? I'm trying to think how to put this without being more of a jerk than usual. I understand right now that this is new. All we're talking about today is effectively jargon. So all of this is new. Mistakes are going to be made. That being said, it is very important that you are able to distinguish between what these different things mean, because when you're talking to an electrical engineer working in the power industry, they're not going to say a voltage VAB or anything like that. They're going to be like, oh, hey, we need to measure these line voltages, we need to measure these phase currents, all of that kind of good stuff. When you work problems, that's the type of things that you're going to be asked. So having an understanding of what these quantities are, what they represent, all of that kind of good stuff is critically important to you being successful in this last portion of the course. So having questions about stuff now, perfectly acceptable. It's new. Not understanding what's going on next week, very, very problematic. So if something is confusing now, let's get it sorted. Is all I'm trying to get at. All right. So we've talked about the Y connected source. I'm going to just draw or label these currents IAA, IBB, and ICC. And for what it's worth, these line currents will literally be the same for every configuration, so I will never write these down again. There's no point. Okay. Now let's talk about a delta connected load, or excuse me, delta connected source. Once again, we are going to have a conventional way that I absolutely hate, and then what I feel is more simplified representation that I will wind up using. Okay. So let me see if I put A on top up here. I did. So here's my A terminal. Here's my B terminal. Between A and B, I'm going to have a voltage source. I'm going to put my C terminal down here. Between A and C, I'm going to have a voltage source. And between B and C, I'm going to have a voltage source. So this is the common representation. Okay. Let's go ahead and fill in some information here. So this is going to be the voltage VAB. This will be my voltage VBC. And this will be my voltage VCA. So in a Y-connected source, all of our negative polarity terminals of our voltage sources were tied together at that common neutral node. Now we have things rearranged so that the negative polarity terminal of each voltage source is touching the positive polarity terminal of the subsequent voltage source around like this. There is no neutral connector or neutral conductor whatsoever. Now, the way that I prefer to represent a delta connected source is actually like this. So here's A. Yes.
If there's no neutral connector, then is there plenty of phase voltage here?
There absolutely will be. We'll talk about that in just a second, but yes. You are starting to catch on to why this nomenclature and everything can be such a pain in the butt. So this will be our voltage VAB. This will be our voltage VBC. And this will be our voltage VCA. All right, so let's more formally answer Patrick's question here by identifying our phase voltages for this particular system. So by definition, a phase voltage is nothing more than the voltage drop across one phase of our source or load. So for a voltage source, that's literally always just the voltages that are provided by each source. So our phase voltages will be VAB, VBC, and VCA. It literally can't be anything else because those are our voltage sources, each one of them representing one phase of our three-phase source. So they literally have to be our phase voltages. David.
So on the right-hand side diagram, your VCA is the positive polarity on top or bottom?
It is on bottom. I will redraw that so that it is more clear. Plus on bottom, minus on top, squiggle in the middle. And I'll draw this one because it looks crappy as well. So now let's talk about our line voltages. Just to reiterate what we learned 10 minutes ago tops, a line voltage is nothing more than the voltage drop measured between the transmission line terminals of our source. Okay? So what should our line voltages be here? They are literally the exact same thing as our phase voltages. So I can draw them on here like so. And over here, like so. So this is where things can kind of get a little confusing, right? So for a Y connected voltage source, our phase voltages and our line voltages represented very different quantities. But here in a delta connected source, our line voltages and our phase voltages are literally the exact same thing. What we're going to find out when we look at a full system is that effectively, when we're dealing with delta connected anything, line voltages and phase voltages are the same. And when we're dealing with Y connected anything, line currents and phase currents are going to be the same. There might be a little mix up on the sign, but we'll sort that out. All right, so now let's talk about our phase currents. So phase currents are the currents that are flowing through one phase of our voltage source. I am defining our phase currents to be flowing into the positive polarity terminal exactly like I did for our Y connected source. So we are going to have a phase current here flowing into positive polarity terminal of VAB. We'll have a phase current here, IBC, And we'll have a phase current here. ICA, you may also hear these referred to as delta currents. On my other representation, we have our current IAB, IBC, and ICA, like so. So that's our delta connected source. All right. Y connected loads. So now that we're addressing loads, all of our subscripts are going to be capital letters because we're on the load side of the system. So we might see something like this, where here is capital A. Here's capital B. Down here would be capital C. This point of interconnection is our load side neutral. It is once again an optional quantity. I'm going to call this impedance ZYA. So this is the A phase of a Y connected impedance. Here's ZYB, and here is ZYC, like so. And then on my preferred way to represent these things, it would just look like this. So we have A, B, C, and N. Here is ZYA, ZYB, and ZYC. So I would like for one of you gentlemen to tell me what you think our phase voltages will be. What do you mean by the same?
Like still VAB, BBC, and then BCA.
So those would be line voltages because you're talking about voltages measured directly between transmission lines.
Okay,
But it'll be capital letters this time. But yes, absolutely. So VAN, VBN, and VCN. So here is where VAN would be, where VBN would be, and where VCN would be. All right, Patrick. What are our line voltages going to be?
VAB, DC, DC.
Yep. All with capital letters. And what about our phase currents? Absolutely right. So just the current flowing through one phase. So this guy right here is IAN. This right here is IBN. This one right here is ICN. Oh, 100% correct. And because we only have less than 3 minutes left, we'll cover Delta connected loads on Wednesday. That being said, it's effectively going to look like the exact same thing we have for Delta connected source, except that all of our subscripts will be capital letters. And then I'll draw all the things on the picture. All right. There is not any homework assigned with this because we didn't really do anything other than talk about the jargon and all of that kind of stuff. It is my goal to have you guys' filter design project posted before I leave for today. And it will be due on Friday because I believe the take-home portion of your test is due Wednesday. And then that way, when I assign homework on Wednesday, it'll be due Monday, and we'll be back in the swing of something's due every damn day. So it's on the syllabus. As far as I know, it's the last day of class, which might be the 22nd of May. So a week from Wednesday, yes.
So it's the final exam, have to take on portion in it.
I will give you that take-home portion probably on this upcoming Friday or something like that. Yeah. If I don't wind up just putting it out either today or on Wednesday with your first homework assignment. Alrighty, see you guys on Wednesday.